I'm going to go over some quiz questions, a couple quiz questions that are important. We're going to do some derivative rules and derivatives of composite functions. Also in here is transcendentals. We have there'll be more derivative rules. And then we're going to do the calculator work, which will be derivatives. Okay? All right. So, okay, so quiz 3 review. All right, this question. Promised you this question would be on it. It's going to be on everything. How do we do this question? You need the equation of the tangent line, so you're going to need to do the derivative. And what's the derivative of this function?
2x minus 3.
Y, so I'll write y prime equals 2x minus 3. Is that the slope of the tangent line? It is, but you have to give it at a specific value. What value do you want?
5.
Which value here?
X value in the bracket.
You want it to be minus 2, right?
Yep.
So what is that? That's going to be minus 7. That's the slope. What's the point? You need a point for a point slope formula line. Do you have a point? You have an x value, right? What's the x value? -2. How do we find the y value? You plug it in. If you want the y value, you plug it in, plug -2 into the y value, which would be -2 squared minus 3 times -2 is what?
10.
4 plus 6 is 10. So that's the point. Okay, then you use the point slope formula, which is y minus y1 equals m times x minus x1. So you get y minus 10 equals -7 times x plus 2. Now you have one other thing you have to do, because that once it is y equals, you have to get rid of that minus 10. How can you get rid of the minus 10? Just add 10 to both sides. That's it. Put that in your calculator and you're good.
So this connect is this issue then. Some answer was like -8x plus -10, and I put the answer, it was wrong. And then I had to take out the minus outside and add like 8x plus 10, and then it accept the answer. I didn't.
Okay, so
3 questions like that.
that may be.
I don't know what's the issue with the
But sometimes it takes stuff and sometimes it doesn't. That's a programming issue. And with all these programs, the programmers can only put so much intelligence into them. So if it marked it wrong, but it was right, if you were to take it on a test, I would fix it. Okay, I would, if you wrote it on the paper the right way and it marked it wrong, I would see it on the paper and I would change it. Okay. Okay. So here, so you can do this the way we did it with the quick and dirty rules, or you could do it by using the definition of derivative. That's what Connect tells you to do. And if I told you before, what is the purpose of college? It's critical thinking. I want you to think for a second. Just because Connect wants you to do it that way doesn't mean you should do it that way. Okay? Connect doesn't know how you do it. It only knows to explain it to you this way because this question comes up earlier before we do the quick and dirty rules. But you know the quick and dirty rules, and it doesn't know what rule you use. And I'm the one who grades your paper when I grade the paper, and I am perfectly happy with the quick and dirty rules. Do not try to be a hero and do the definition of derivative by hand just because Connect does it that way. Okay? Don't be trapped doing it just because Connect does it that way. You understand what I'm saying? Let it go. All right. All right. So here's a question that you might see. Just a note to you. The questions on the exams come from the homework in this class. They used to come from the quizzes, but now your quizzes are homework, and the quizzes that used to be quizzes are now homeworks, And I've written new quizzes for you that are only 3 or 4 questions. Okay, but the questions are pooled. What a pooled question means, it grabs questions from a bunch of questions that look the same and test the same skills. This particular question looks like another question and in the homework that you may not see until we get to an exam, and then you might get this one or the other one. And so I just want you to be prepared for that. If you want to see every question, you have to do the homework. Okay? And then every question will look like the ones on homework. So if your word problems aren't your favorite, then look the other one up. But this particular one makes a lot of sense if you read it. All they're saying is if you're being taxed at 15% for your first, whatever, $18,000, they want to make sure what they're saying in this limit thing right here is saying, as my salary approaches no dollars from the positive, which means I'm making less and less money, how much should you pay in taxes? If you make less and less money to the point where you make nothing, how much do you think you should pay? You should pay nothing. And this is the tax record. It says if you make less, the tax function, if you make less than 18,200, you use the top line. If you use that top line and you're approaching 0, you just put that top line into the limit. And since x is going to 0, what are you going to end up with? If it's a is some number plus something that's going to 0, what do you end up with? A plus 0. So, and that has to end up being 0. So what is a going to be? A is going to be 0. Okay? All right. All right, so what I would do is I would say, right, the limit is x goes to 0 of t of x equals a plus 15 times 0, so it's just going to be a, and that's going to be 0. So then you know a has to be 0, and that's the answer you put in for a. For b, okay, it says that this limit, all they're saying is the limit has to exist. So that means the limit has to be the same on both sides. So you're going to end up plugging in you're going to say 18,200 with the minus means you're approaching it from which side? The left side or the right side? The left side. And which one of these lines of the function are the left side? The top one or the bottom one? The top one is. So you're just going to plug in, you're going to write 0.15x because a is already 0. You already know it's 0. So it's just 0.15x. So if you plug 18,200 into there, into the top function, you end up getting 2730. Okay? And now, if you plug, you do the same thing, except now you're approaching from the right side. Which line represents the right side? The top line or the second line? The second line. So you put the second line in there, which is b plus 0.11x minus 18,200. And you have the limit is 8, it's going to 18,200. So when you plug that in there, what are you going to get? 0 for that, 0.11 times 0 is 0, so you're just going to end up getting b. So b you get on one side, and 2730 you get on the other, so b must be 2730. Okay, it kind of makes sense because what it's saying is you have these two different tax rates, but if someone's making 18,200, you want them to be just the same on both sides. Okay? That's what they're trying to say here. Some of you will memorize this problem and then you'll get it wrong because you have to show some work here. You really have to do something. Because the other one is different answers. The other word problem that's pooled with this one looks similar. Has two little boxes, has an A and a B, but they're not. They're different. That's how you get screwed. Okay. All right. I got a lot of stuff to do, so a lot of rules to go over. So let's start with what is math? Language. What is calculus? Study of change. What are the two rates of change? Instantaneous and average. Okay. What is the instantaneous rate of change? What can you tell me about it? Instantaneous. How many points do you need for instantaneous? 1 point. Okay? And there's another word for it. Say it out loud so I can hear it. Velocity? Yes, that would be the instantaneous rate of change. There's another word for it. Slope of the tangent line. Very good. And there's another word for it. Derivatives. Very good. They all mean the same thing. The velocity is the derivative, is the instantaneous rate of change at the slope of the tangent line. Okay? All right. Last time we went over quick and dirty rules. Just some of them here. Derivative of a constant is 0. The derivative of a line is the slope of the line. You could take the derivative of each part of an equation. If you have mx plus b, you can take the derivative of mx and the derivative of b. If you have a constant times, if you have the derivative of m times something, you just take the derivative of the something and the m hangs out there. You also have the product, the power rule. You have an x to some power. Take the derivative, you could bring the n down and subtract the power. Yes? All right, those some big ones. All right. So can we do these? The first one. Anything special about that one? There's 3 parts to this trinomial. So you can take the derivative of the first one. What's the derivative of x to the 4th? Use the power rule and you get 4x cubed. Yes? Okay, you're going to get 4x cubed, right? The next one, what are you going to get? Let's put a minus there. You take the 2 down, but it's already a number there, 3. So what's 2 times 3? 6x to the first power, or just 6x, right? Oops, so what's the derivative of 7? Derivative of a constant is 0. Okay? I'm going to give you a hint, or not a hint, some advice. This is one of the few times I don't need to see a whole lot of work. You can do this. A derivative of a polynomial like this can be done without showing me any work. Okay? The next one, though, needs work. Okay, when you look at it, you say, I don't know what to do with that. But you might if you remember some algebra. If you have if you have 1 plus 2 plus 3 divided by 4, couldn't you do just 1 divided by 4, 2 divided by 4, 3 divided by 4? Right? So that's what you could do here. You could just break it up to x to the 7th over x to the 4th minus 3x squared over x to the 4th plus 7 over x to the 4th. You take the derivative of each one of those. So you could do some algebra. What's x to the 7th over x to the 4th?
X cubed.
X cubed minus, what's that?
3x to the power negative.
3x to the negative 2 plus 7x to the negative 4. So what's the derivative of that going to be? 3x squared. Ooh, what's that? What's that?
6x plus 6x.
It's going to be plus 6x to the what power?
Oh, sorry, negative 2.
If you write it this way, I'll be happier. And then you say negative 1, I'll give you credit for that. But if you say negative 1, it's wrong. Because what's negative 2 minus 1? Negative 3. Oh, curses. Okay, what's the next one going to be? Minus 28x to the,
Negative.
I'm not sure. He screwed me over last time, so I'm going to make it. So it would be 3x squared plus 6x to the minus 3 minus 28x to the minus 5. If you make an arithmetic error, that's no problem. I'll give you credit for that. If you don't say what you're doing and you add a power instead of subtracting a power, then I take points away. Okay? Do you understand what I'm saying? Yeah, they should already be up. All right, what about x, the square root of x? That is x to the 1/2. So what's that going to be when you take the derivative? 1/2 x to the 1/2 minus 1, which is going to be 1/2 x to the minus 1/2, or you could write it as 1 over 2 square root of x. That or thing, that's or. It's not a requirement. In fact, I'd rather you didn't do it at all. If you're asked to find the derivative and you find the derivative, you do not have to continue with algebraic manipulations. You're done. Okay? You will probably make a mistake. I used to tell my students, less is more. And then one of my colleagues said, well, expect less, get less. And I said, but since less is more, I'm getting more. See how that works? So give me less / more by writing less. Just give me the equation. Connect may reject it, but you'd be surprised how much stuff Connect accepts in unsimplified form. It really, sometimes it does really well with it. If it doesn't, then you should just have another chance to clean it up. Okay? On a test, I always take it unsimplified. Okay? All right, so these are just those questions worked out. More rules: product rule, quotient rule, chain rule. Okay? These are all quick and dirty rules designed to make your life easier, so much so that I go over them so fast that your head might spin a little. So give yourself time to absorb these. They will take some time, like we just went over the quick and dirty rules last time, and now I'm giving you 3 more big rules. Chain rule is probably the worst. Okay, and I'm going to give a whole bunch more in transcendentals as well. So I'm just saying, you're going to need to practice these, so don't feel bad today if you maybe you just pay attention and see what you can absorb. Okay, so the product rule. All right, the product rule is for when you have 2 functions, f and g, and they're multiplied together as in a product. Okay, if you want the derivative, you want to know how fast this product is changing, it's the first times the derivative of the second plus the second times the derivative of the first. Sometimes I'll say it the other way around. That's okay for the product rule. You could say that second times the derivative of the first plus the first times the derivative of the second because it's a plus. And it doesn't matter which order you do them in. Okay. The quotient rule, it does matter the order because there's a subtraction. So it's the bottom times the derivative of the top. Bottom is g, top is up. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom square. Okay? I can prove this using the product rule if I had to. But I'm not going to. As far as memorizing them, you should memorize these. Although somebody, I think somebody in my last year, somebody used this, they had heard in their calculus class, low D high, high D low. Low at the bottom is low and high. So low D high, high D low. If you can remember it that way, that's fine. All right, so here's an example of 2 functions that you could use the product rule for. At this point, we only have polynomial functions that we can take the derivative of. So both those functions are polynomials. So the first and the second. So what are you going to do to take the derivative of this? Using the product rule, it would be the first times the derivative of the second plus the second times the derivative of the first. Which is, so it's the first times the derivative of the second plus the second times the derivative of the first. You see how I wrote it out, even though it was a lot of writing for me to do this? I wrote it all out because I don't want to be stuck making a mistake in my head, even though I'm sure I can do the derivatives in my head. Look, they're just polynomials. See, so it's the first, there's the first written all out, and the derivative of the second is 23x to the 22nd minus 2. Plus, then the second is x to the, see what happens when you screw things up? What is that, 23rd? Is that 23rd or 25th? It's the second, so it's 23rd. So easy to make a mistake. You see that? That's 23rd, so this should be 23rd also. 23rd, right? minus x plus, and then the derivative of x to the 50th plus 2x to the 25th plus 7 is 50x to the 49 plus 50x to the 29. 24, sorry. Okay? Any questions on that? So that's an example of the product rule.
You don't solve it?
And you don't have to do anything with it, just leave it. Done. You've taken the derivative, there's no more derivatives to be done. If you leave the second line, you'll get some credit, but you will have left some of it undone. Okay? All right. Remember this one that we just did where we broke it apart? This is I won't say it's a mistake, but you're making something. The way we did it required you know some algebra. Okay, you could also use the quotient rule for this because it has a bottom and it has a top, right? So you could say the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, and then you can do the derivatives and you don't have to remember any algebra. You could leave it right like that because the derivatives are done. If you do play around with the algebra, and you don't make a mistake, so let's say you distribute those, distributing isn't so bad. And then if you break it apart, you end up getting this. So you got, there's a 7x to the 10th and a minus 4x to the 10th. So you can work on it a little bit and you end up getting the same answer that you got the other time. But you could use the quotient rule or you could use the algebra. Okay, if you're going to do some ugly algebra, can I suggest that you check your answer by maybe putting a number in and seeing if it agrees with the calculator? Sometimes the calculator will tell you if it's wrong or not. Okay, be nice to know if it was wrong. All right, remember this one we said find the derivative of 1 over x minus 5. Now you have you could use a quotient rule if you wanted to. If you're going to use the quotient rule, you have to understand that the derivative of the top, see how I wrote it there when I put it in red, the derivative, okay, it's the bottom, it's x minus 5, times the derivative of the top, which is 1, minus the top times the derivative of the bottom, all over the bottom squared. The derivative of the top, the derivative of 1 is 0. It's a constant, yes? Some of you will pretend that that's not the case. You'll be like, oh, it must be 1. Why would all that beautiful algebra go away? Well, it does. And then what's the derivative of x minus 5? This is another one that throws people off. There must be 5 or something, or the x or whatever. Somehow you want to put more than this is just 1. Because that's a line of slope 1, and so the tangent would be 1. Okay, so the answer becomes minus 1 over x minus 5 squared. Remember, we did this one before. So now we could use the quotient rule. There's still going to be a better way to do this. Coming up soon, very soon. Okay, here's one with 1 over x plus 5 squared. You could use the quotient rule for that one also. Okay, all right. And that's in the notes if you want to do it. All right, so coming up soon, the chain rule. Okay, the chain rule is for taking the derivative of a composite function. So what is a composite function? It's an assembly line. Okay, what is a function? What's a function? It's a job, right? It's what you did in pre-calculus. When you do a composite function, it's 2 different functions, f and g, and one of them is so you're going to give x, will be the input, and it'll go to the g first. It goes to the function that's closest to the f. So see this f of g? G gets it first and does whatever its job is, and then passes it on to f. Okay? G, I'll call G the inside function and F the outside function. But there could be more of them. There could be something like F of G, of H of X, in which case, whoever's closest to the X goes first. Okay? I used to do this, just, I used to, when I got this job here, they asked me about this. And I used to think that this was like a big fish eating a little fish eating, you know how it's like big fish eating, which is that's not really what happens. What really happens is the G fish eats the food, and then the G fish isn't eaten, the F fish eats the G fish's poop. Okay, I know, it's gross, but that's what it does. The smaller fish has to produce a product. The fish isn't eaten, the product is eaten. It's passed along like an assembly line. Okay, does everyone understand that? So the first thing is to identify which fish, who's the inside fish and who's the outside fish. Okay. When you take the derivative of, when you want to know how fast is a composite function changing? Okay. The derivative of a composite function, we have an outside function and an inside function. That derivative is going to be equal to the derivative of the outside function, where you leave the inside function alone. Okay, times the derivative of the inside function. Okay, I tried to explain this using, with my other class, we watched that I Love Lucy, the chocolates thing. Do you remember? Does anyone, okay, Amanda's old enough to remember the I Love Lucy with the chocolates thing. They work in this factory and they're told if they can't keep up, they have to take chocolates. They come from one and they put them in a wrapper and then they go the other way. And so the input is a chocolate and the output is a chocolate with a wrapper on it, and they're just the middle guy. Okay, and what happens in this episode is that the chocolates come too fast and they start eating them and shoving them places and stuff. You should watch it, it's funny. Anyway, we're talking about calculus is the rates of change. How fast is something changing? If you have an assembly line where chocolates are coming in and you have to put wrappers on them, okay, the rate at which the wrappers are coming in could be increasing, but maybe they're just coming in at a very slow rate. In which case, if you're putting wrappers on them and they're just coming in very slow, but let's say they're increasing, slowly but increasing. When you're putting wrappers on them, your output isn't going to be very fast, okay? But your output depends on not on how fast it's changing, but what is it? How many chocolates are coming in? And then how quickly you can turn them around. So this is how quickly you can turn them around by how many chocolates are coming in. And then this is how quickly the chocolates are increasing. If the chocolates are increasing, then everything's going to turn around, right? Because they'll come more and you'll be able to get more out. So there's two things going on here. One is that how quickly the chocolates are changing, which is what's coming in, and then how quickly you can process them, given how many there are. Yes, sir.
So why cannot we use the product rule in this?
This is not product. This
But it
is
looks
a
like-
product, but this is not the product rule.
Okay.
This is a function inside another function. You'll see. Let me give you some examples. But don't be fooled. In the end, it is a product. It's a multiplication thing.
Yeah.
Okay. So I'll put this in words. The derivative, you're going to take the derivative of the outside function and you're going to leave the inside function alone. And then you're going to multiply it by the derivative of the inside function. Okay, so let's first work at identifying some inside functions. Okay. All right. Here, this is, okay, you would never want to multiply this out. This is something raised to the 100th power. Do you see an inside function and an outside function? The outside function is the 100th power. The derivative of x to the 100th power is going to be 100x to the 99. Okay, but we're going to put g to the x inside there. And that's our inside function. And then we're going to multiply it by the derivative of the inside function. All right, so the inside function here is all of that polynomial, right? This whole thing, x squared plus 3x plus 8. So we're going to leave that alone. So we take the 100 down, leave the inside alone, raise it to the 99th power. Then we're going to multiply it by the derivative of the inside function. Okay? This is how quickly you process the chocolates coming in, and this is how quickly the chocolates are coming in. So you multiply here, and this is x squared plus 3x plus 8. The derivative of that is 2, that's x squared, so it's 2x plus 3. Okay, and since this is all multiplication, I could put the 2x plus 3 in the front. Okay, you know what? We have the power, because this is a smart board. I could actually put that there. I mean, that's what it is. It goes right there. Okay, any questions on this? Let's do some more. You will get more comfortable with this. Like, so this is the same thing. Something to the 100th power is 100. That's something to 99 times the derivative of that something. If it's just x, the derivative of that something is just 1. Okay? Here's some things to note. If you've got, so this is where we're going to use the chain rule again. This is actually going to come up a few times. If these variables, you know we talk about take the derivative and sometimes use a prime. If you use the prime notation, it means the derivative of with respect to whatever variable is there. If you use the calculator, it asks, what variable are you talking about? When these variables don't match, this is a chain rule. There's a function in there, they're just not telling you what it is. It's some y value. It's on a need-to-know basis. So what's the derivative of something, of y to the 100th? We don't even know what y is. So we just say we bring the 100 down, y to the, oops, the 99 must have gone away. 99. And then we leave the inside alone, we leave the y in there, and then we just multiply times dy dx. We don't know what the derivative is, we just write it that way. Okay? Please note, pi is a constant. You understand this? 3.141, we're gonna have a pi day in a couple months, big celebration, it'll be wonderful. No, we don't. But if we did, it would be March 14th, spring break. Okay, take the derivative of this. You bring the 3 down. You take a power away. Then you multiply. Since the variables don't match, you get d pi dx. Oh, pi is not a variable. It's a constant. So how much is pi changing with respect to any variable? It's 0. This whole thing is 0. So even if you do use that power, if you do use the chain rule or the power rule or any of the rules, this is still 0. This whole thing is 0. You don't. Sometimes you'll be suckered in. Where's my suckered in examples? All right, I'll get to them later. All right. Here's another thing. Remember that one that we did before? We've done like 3 times. One, we used the definition, and then we used the quotient rule. Well, you can also use the chain rule. Thank you. You see, if I change this to 5 times x plus 2 to the -1, I can just bring that -1 down and make it -5, leave the inside alone to the -2, and then multiply times the derivative. And I get the same answer. That was fast. I think that's the fastest way of all. Okay, it doesn't even require more than 2 lines. Okay, if you want, the other one I had x plus 5 squared, same thing, x plus 5 to the -2, you bring the -2 down, subtract the power, take the derivative of the inside, leaving the inside alone, and then taking the derivative of it. Okay? All right, let's see what else we got. Oops, transcendentals. All right. Transcendental, do you have a question? Okay, the question is a good question. It is, do you have to write in d over dx? You don't. If you write a little prime, like a lot of people like to use the prime, is that what you're going to use? It's okay. As long as you understand that by writing a prime, you're taking the derivative with respect to whatever variable is in that function. So if it's x, then it's x. If it's t, then it's t. But I'm writing it this way so that you can see that this is derivative with respect to x. So you can just write a little prime if you want. Okay. Something. So here's some transcendental functions. There's any transcendental functions are the functions with letters in them. So don't confuse the letter with the fact that it's not a variable. That e is not a variable. That e comes from pre-calculus. Remember the exponential, right? The natural log is part of it. It's a cousin of pi. It's about 3. It's 2.71. So anyway, and the natural log of it would be 1. By the way, so if you have e to the x, you want the derivative of e to the x, it's e to the x. You want the derivative of a to the x, it's a to the x natural log of a. You want the derivative of the natural log of x, it's 1 over x. You want the derivative of the natural log of the absolute value of x, it's 1 over x. You want the derivative of sine of x, it's cosine of x. What do you think the derivative of cosine x is? It's negative sine of x. Who knew that? Well, you had calculus before. Anyway, these are some of them. There's more. There's a ton more. Okay, there's tangent is secant squared, and there's a regular log one, and the derivative of secant is secant tangent. So what am I telling you? I'm telling you that I'm just throwing them at you really fast. And it's like when you have to memorize a lot of things in biology, I'm not expecting you to memorize them right now at this moment. If you can, that's great. If you can't, that's okay too. But you see the ones with the stars next to them? These are the ones you need to know. I will not give you these on a test. Because if you leave this class not knowing that the derivative of e to the x is e to the x, you will embarrass yourself and me. Okay, you'll bring shame to the family. Okay, everyone knows this one. The second one, the derivative of a to the x, people don't always remember that one. You could probably Google it really fast. You know, some things you can Google and people are like, okay, but if you ask Siri, what is 3 plus 7? That's okay. Except anyone around you is going to be like, oh my God, did they have to Google what 3 plus 7 was? You'll embarrass yourself. So this is high end. Most people who haven't had calculus will not be like, she didn't know what derivative of e to the x is. What's wrong with her? No, it's derivative of e to the x is e to the x, but you should know this. You should also know the derivative of sine is cosine, and derivative of cosine is minus the sine. Okay, I won't tell you those. Mostly I tell you stuff during a test, but I won't tell you those. But if you ask me what's the derivative of tangent, I might tell you during a test. If you can Google it and you can tell me what it is, exactly what you want, I'll probably tell you. Derivative of natural log of x, that's another one you have to know. The derivative of the natural log of x is 1 over x. Okay? And these are the ones you don't have to know. Derivative of secant is interesting, but you don't have to know it. So you understand I have 4 of them you need to know. E to the x, natural log of x, sine and cosine. Okay? All right. So what's great about transcendental functions is all the ones we did so far with like the chain rule, they just had polynomials. But now that we have these that we can do derivative, now we can have transcendental functions. So you have to understand, if you take the derivative of e to some stuff, I'll call it crap because that's what it says. That's e to the crap, that's a turd. If you want that, that's e to the same stuff, leaving the crap alone, and then take the derivative of the crap. Okay? It's just a chain rule with the transcendental. If you want the derivative of the natural log of some crap, the derivative of natural log of x is 1 over x. So the crap stays in, it goes there for the set of the x. And then you take the derivative of that crap. Do you see a pattern yet? The derivative of the sine of some crap is what? What's the derivative of sine? Cosine. Leave the crap alone and then take the derivative of the crap. Are you with me on this? I'm sorry. You know, crap just followed me over the years. Leave it alone and then take the derivative of it. Okay? All right, so let me just say this. Somebody's going to ask me this, like, how do we know the derivative of e to the x is e to the x? Well, we go back to the definition. Remember the definition. If you want the derivative of e to the x, it's the limit as h goes to 0 of e to the x plus h minus e to the x all over h. And we have e to the x plus h. You could break that up algebraically to e to the x times e to the h. Then you can factor out e to the x. And then you have this whole thing, the limit as h goes to 0 of all of that. And if you wanted to, you could put that in your calculator and figure out that it's 1. So the whole thing turns out to be e to the x. Or you could use L'Hopital's rule, which we haven't done yet, to show that this is 1. Okay, there's various ways of showing that this limit is the case. We will not be using the definition of derivative pretty much at all. But every time we get a new function like e to the x, somebody had to get those, all those ones I said memorize. Be glad I don't tell you to prove them, because this is how you would prove them all. And some of them are much harder than others to prove. Okay? You don't have to prove them. No one's going to ask you to do them. You will not embarrass anybody if you don't know, remember them. So that's okay. All right? But this is why we use the definition, so we could get those. So I'm just quickly throwing them at you, and you'll remember them eventually. Okay? But they're done by proofs. All right. So here's some functions. There we go. I see e to the x squared. Do you see a function inside another function? Sure you do. What's inside? What's the inside function? X squared is the inside function. So what is the derivative of e to something? E to the crap. What is it going to be equal to? E to the crap times the derivative of the crap. Okay? Are we good with that? What's the derivative of the natural log of crap? Do you see an inside function? What's the inside function? So it's going to be 1 over x plus 1 times the derivative of x plus 1. Okay? Now this one's the hard one. What's the inside function there? Who's inside of what? You know why? Because you probably didn't cover this in your pre-calculus class, or maybe you did, but you don't remember it. What does that little 2 mean?
So it's gonna assign x squared.
Okay, so hold on a second. Do you remember when you had sine to the -1 power? Do you remember? So maybe you didn't have me, so you don't remember this, but what does that mean? That means the inverse sine. What does this mean? This means what? This means cosecant. Is that what you wanted to say?
Yeah, you don't calculate this thing.
Right, it's 1 over sine, which is cosecant, yes? Oh, it is, you remember that now. Yes? Okay, I was just trying to skip a step so you could be all impressed with my knowledge. No, don't care. But anyway, do you understand? We had a notational issue. That's sort of why we invented cosecant, so you wouldn't confuse it with that negative power, right? But when we put a 2 in there, there's no confusion with inverse. It means something very specific. When we put another power in there, we mean very specifically, when we say the sine squared of x, we mean this. We mean the sine of x, that quantity squared. The whole thing. Do you see an inside function here? Is there an inside function? What's the outside function? The what? The squared is outside. This is the inside function. Aha. All right, so let's see what we got. So if we write it that way, when we go to do the derivative, we take the derivative of the outside function, which is what? The derivative of the outside function, it takes the 2 down and puts it in front, right? So you get 2. Subtracting 1, you get 1, and leave the inside alone. And then do what? And then take the derivative of the inside. That's the derivative of the sine of x. Okay? You with me on that? That one is so evil and so oftenly put on tests.
What if there was sine -2 of x?
Sine to the -2 of x, that would, okay, so if it's not specifically -1, that's the only one that means inverse. -2 would mean 1 over that squared.
So 1 over sine x2.
So if you, what he's asking me is this: if there was a minus there, it would mean this, the derivative of 1 over the sine squared of x, which would mean 1 over the sine of x squared. Okay, but only as -1 that is the problem. -1 means the inverse. -2, that's just that I don't know if you're ever going to see it, but you know, if you're a business major, it might come up. Never. So let me just get rid of that. All right, what about this one down here? So we did all of those, but what about this last one? What do you think the inside function is there? As it is highlighted in yellow, what's the inside function? It's the x squared. So here's all the derivatives and stuff, but this one, if you want the derivative of the cosine of x squared, what's the derivative of the outside function is cosine. What's the derivative of cosine?
Negative.
Minus the sine, leave the inside alone, and the inside is x squared, so it stays there. Then times the derivative of the inside is x squared, so you get 2x. Okay? Here's all of them done. Okay, any questions on this? So you identify the inside function and take the derivative of the outside function. If you want to know a rule, and I don't have it written down, but remember, please excuse my dear Aunt Sally?
Yes.
It's the reverse of that. You take the derivative of the outside functions first and you work your way in, as opposed to going inside out like you would do. Please excuse my dear Aunt Sally. So in this case, which would you do first, the cosine or the x squared first? You would do the x squared first and then the cosine next. So you do the derivative in reverse order. You do the cosine and then the x squared. Okay? Whichever would come first in please excuse my dear Aunt Sally comes last in derivatives. Okay, here's some tricky ones. Okay, let me just fix this one here. See that little prime there? I'm going to take that out. Oh, did I take it out? I took the wrong thing out. No, oh, whatever. These are tricky because what's the derivative of the sine of pi over 3? What's the derivative of the sine of pi over 3? I know you're thinking derivative of sine is cosine, blah, 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 blah. No. Sine of some value is just some number. What's the sine of some number? A number. And what's the derivative of a constant number? 0. And the second one, you have some unknown function, f, times the sine of pi over 3. Do you want to use, let's say, a product rule? Because that's multiplication? No, you don't. Because why? Because sine of pi over 3 is a constant, so it just hangs around. You could use the product rule, but why not just make it, just write the sine of pi over 3 like it was the number 2. Just leave it there. Take the derivative of the f. What about the second one? There's x. There you have, you're given the function. So what's the derivative going to be? Okay, so y prime equals 0. Here, y prime equals f prime times the sine of pi over 3. And here, what's derivative going to be? What's x, the derivative of x to the 1/2? That's 1/2 x to the minus 1/2 times the sine of pi over 3. Because it's a constant, you just leave it there. Okay?
Can you tell how you do the third again, please?
What third? The third one?
Yeah.
This right here means x to the 1/2 power.
Oh, x to the power 1.5. Okay, now.
So I bring the 1/2 down and I subtract 1.
Just write it.
Yep. That's all. It's just 0.5. Okay. All right. If you want to know the sine of pi over 3, it's like 0.68. So the derivative would be 0. And you could just write 0.68 instead of the sine of pi over 3. Okay. All right. All right. Here's something else. The derivative of sine over cosine. Okay. sine over cosine is a quotient, so we're going to use the quotient rule. Again, I don't expect you to do this every day. If you're walking down the street saying, oh, look, there's a sine over cosine, I'm going to take the derivative of that. Okay, let me get to the point. Let me just show you. If I use the quotient rule, it's the bottom, which is cosine, times the derivative of the top. Derivative of sine is cosine, minus the top, which is sine, times the derivative of the bottom, is derivative of the bottom, minus sine. Okay, so I can just, so minus times a minus, so I end up with cosine squared plus sine squared. And what's cosine squared plus sine squared?
1.
That's 1 from pure pre-calc. That's the one of those identities. Diagonal identity. You forgot. You better remember that. No big shame for the family. That's one of the few things you have to remember from pre-calc. Sine squared plus cosine squared is 1. Remember your kid being 1 year old and saying, happy sine squared plus cosine squared. The first birthday. Anyway.
No.
1 over cosine, so you end up with 1 over cosine squared. And what is 1 over cosine? Secant, so this is secant squared, right? That's a trig identity, that 1 over cosine squared would be secant squared. What is sine over cosine? Remember a trig identity for sine over cosine? Again, another one that you needed to know. Did you say tangent?
Yeah.
Very good. That was good. So the derivative of tangent is secant squared. Well, I didn't need to know this one. I could have figured it out with the quotient rule. Okay. There were times in my life that I've been asked to do ridiculous things. And this was before Google and before Siri and before actually before they gave you formulas or anything. If I was asked something on a test and I had to figure it out, I could always go back and figure it out. But if you know those 4, you're in good shape. This one lets you know more of them. Okay, the derivative of secant of x. I just want to say this one you're not likely to see anywhere. But I like to go over it because remember how I say the derivative of the outer function is something and leave the inside function alone? This is a weird one because we don't have, remember how I said like 1 over cosine squared was secant squared, like you had a function to match the answer? If you do the derivative of secant, which is 1 over cosine, and you use the quotient rule or whatever, you end up getting tangent secant. Tangent x, secant x. So when you have some crap on the inside, you see the inside function here is x squared, and I say leave it alone, derivative of secant is secant tangent, you write secant x squared tangent x squared. So the inside stuff gets written twice. That's only because we don't have a function that describes it in one way. But we need both of them. We could just make up a new function, and mathematicians love to do that. We could have done that, but we don't. And since we don't, you have to put the x squared in both of them. Okay? All right. This used to be my favorite question, but and some of my students in my other class were asking me, like, are you going to put that on the test? What am I going to put on the test if it's not in Connect? Is it going to be on your test? No. So that's the deal. So you should not feel pressured to learn all those little things that I like you to know. The reason why I like you to know what math is that going to be on your test? No, but I go over it every single day because I don't want you to embarrass yourself in front of your 2-year-old when they say, what is math? And you're going to be like, I don't know. It's something I took in college. You know, you should be able to answer some fundamental questions about what this course is. Why is it different from pre-calculus? I would like you to know that. That's my own personal agenda. But all right, so speaking of my own personal agenda, let's get into our groups and get ready to present our limit stuff. Okay? And then we can move on to the derivative stuff if we have time. But first I want to do the limits. Okay. Okay, so for this week's group work, last time you put the data in, you found the quartic regression. And then you put y1 equals that quartic regression, so it was in your calculator, right? And then you put for y2, you said find the derivative. Okay? Okay, so this week we're going to do next week we're going to do second derivatives. Oh, then you go to the table and you put a point of interest in and you can get the function and the derivative. And if you do that, you could, you know, for this one right here, hold on. The point of interest here is 2 and the function is 3 and it's changing by 5. Okay? So it says in the second year, according to the LN regression, our revenue is growing at a rate of $5 billion per year. Okay, that's what you could say from last week, but that's not going to be enough for next week. I want second derivatives also. To get a second derivative, you have to do something else. Let me just go on. So these are some examples of first derivatives, first derivative. But for the posting and for you guys for second derivative, you're going to pick a point of interest like 2020, and you're going to have some picture, and you're going to have a third column. And that third column is going to be the second derivative. Okay, so it's going to be, so the math is going to be y. So if you look very carefully, let me just show you this. This is y1 evaluated at 2020, and it equals the a value that came from here. This is y1 prime, so it's a derivative, and it's the b value, it comes from here, and it's also evaluated at 2020. This is y double prime evaluated at 2020, and that's going to come from there. Okay? So what it's going to say is, according to the quartic regression at 2020, x equals 2020, near 20, the function is a. It's changing by b, and don't forget the units, and is if c is positive, it's accelerating. If it's negative, it's decelerating. Okay, that's all you have to say. I don't expect you to report the c value. Just if it's positive, it's accelerating, and if it's negative, it's decelerating. That's what you're going to do next week. That's what you're going to present next week. You just have to say that. Now, the problem with this is I make you do the quartic regression because it's the evil one. You can't put the quartic regression in your calculator and expect it to find the derivative. It won't do it. So what you have to do is, you know how you have a function and you have ax squared and bx to the first and c. If you want the derivative, you're not going to want to copy a down. A is some ugly number, right? Look at this. Look at how big and ugly the number is. Oops, doesn't say. But they're big, ugly numbers. Look at that. Blah. You are not copying that in the calculator. This is what you're going to do. If you have x cubed, you're going to bring the 3 down and put it in front, like you would do the derivative. So it's going to be 3 times a. Ooh, that's ugly color. So it'll be 3 times a. So you're just going to insert a 3. And then you're going to knock a power down, and you're going to insert a 2 and knock a power down. And that's how you're going to do it. And you only have to do it for the quartic once, because once it becomes a cubic, the calculator will be able to do the derivative of it. So so we're going to estimate that long number? So it'll look like this. So here's what this is what I'm expecting to see. There's your graph. Someone's got to label this the number 2. Oops. Hold on, Amanda. I know what you're asking. So this is the number 2. Okay. You put y1 is the quartic regression. Here it is written out in the old format. And then you see what I did was I inserted a 4 times in there, and then I knocked it down by a power. And I went and I did that with every single one. I put a 4 in front and knocked it down a power. Then I put a 3 in front of this one and I knocked that down to 2. And I put oops, hold on, this is really messy. Okay, if you look in the calculator, you can see it here. Here's a 4, and I brought it down in front. So now there's a 4 in front, and the power is 3. So I lopped 1 off. Then the next one, I put a 3 in front and lopped a power off, so now it's 2. I did that with this cubic one. And then with the squared, I put a 2 in front, and I lopped it off and made it a 1. Okay, then for the That was for the 2. For the 1, I just leave the number, and this is x to the 0, so I can get rid of it, and the rest is a constant, so that's 0. So I just get rid of all of that. So I do that in the calculator, and that's all. All I want you to do, the exercise here is to do the derivative in the calculator by hand. So you're just bringing the number down like you're doing a regular derivative, 4x cubed. Instead of x to the 4th, you bring the 4 down, but you're not touching any of those ugly numbers. You're just going to leave them be. Okay? And then by doing that, you get the first derivative and the second derivative. You do it. So, okay. So let's just show you, to show you how not difficult it is. So you can't do it this way. You see how I have n derivative? You can't do it that way. It won't work. So this is what I do. I go down to the second one. Let me clear that out. I do vars 5 arrow over twice. Where'd it go? What happened? Why did it do that to me? That was interesting. So I come down here. I'll try clear again. Clear. I'll do vars 5 arrow over twice, enter, and it should copy see the exact same equation, quartic regression. This is what you have to do. It's tedious, but it's not the worst thing in the world, and it requires not making a mistake on the calculator. You go second delete, which is insert. You see how it's blinking? Then I can put 4 times in there. See it? Then I can go down to where it says x to the 4th power. And I can literally just type over the number 3. And then right next to it, I do second insert 3 times. Be very careful because it's very easy to type over something and then it won't work. Then that 3 has to become a 2. And then here I have to do second insert 2 times. La-di, 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 boop, 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 1. And then it's going to be 1 time, so I don't have to do that. Then it's x to the 0. So I'm just going to take this x and I'm going to hit delete. And I'm going to delete everything afterwards. Okay, that's going to give me the first derivative. And then for the second derivative, I'm good. Okay, so what am I saying? So now if I go to my table, and I go second table, and I put in a value like 0. I forget what this is. In the year 0, we expect that Lady Gaga was in debt by $73 million from shoes, I'm sure. But she was making money, and because this is positive, it was accelerating. Okay? So that's the sort of thing that I want to see. So I need that third column. Okay? All right. If you want to take a minute to do that while I pull up the limits, see if you can do that.